我们非常荣幸邀请到演讲嘉宾 Endura Technologies 执行副总裁、首席产品官 Davud Yazdani 先生。Davud Yazdani 先生将为我们带来题为更智能的电源，实现可扩展人工智能的关键的精彩分享。For our next session, it is our great honor to welcome our speaker, Mr. Davud Yazdani, Executive VP, Chief Product Officer at Endura Technologies. Mr. Davud Yazdani will share his insights titled Smarter Power, the Key to Scalable AI. Ladies and gentlemen, please welcome Mr. Davud Yazdani.
Hello, everyone. How's everyone doing today? I'm sure many of you guys are wondering why there are so many power people these days at AI conferences. Well, I have an answer for you. AI made power sexy again. And today I'm going to show you exactly why. So, in the AI era, we have a simple equation here. Save power is reclaim compute. And reclaim compute means more revenue, more scalability, and ultimately more AI. So when you claim wasted power, you don't just save the energy, you convert that energy into two things. One, revenue, by generating more token from those watts that you saved. And second would be a scalability, by deploying more compute for the fixed power budget that you have, for the fixed facility that you have. And everything that I'm going to show you today comes from this simple equation. So here is the problem in one chart. The blue line that you see here is the grid power generation estimate, how fast it's going to grow by the end of 2030. Is roughly 3.6%. The red line is the data center demand. It's projected to be almost 6 times as grid growth that they are expecting to be. And the orange line that is shooting up, that's the AI demand alone. That's 22 times faster than the grid. Just to give you guys some number to give it some perspective here, the IEA estimates that data center demand could be reached to 1,000 terawatt hour. Do you guys know how many zeros 1,000 terawatt hours has? 15. And that's equivalent to annual electricity consumption of a country like Japan. IMF is even, the number that they are projecting is even much higher than that. It's 1,500 terawatt hour. That's electricity consumption of India. So you see here, the grid cannot keep up. The core challenge in scaling AI, in my view, isn't just generating more power, more and more power. It's how efficiently we consume the power that we already have. That's the budget that we have. And all the data centers, they have to work within the budget they have because they cannot scale the grid so quickly. They have to go through lots of regulatory issues when they want to expand grid, and depends on the region, depends on the country. So before we go into details, historically, the way we measure AI hardware performance, it was in flops. But that's not how data centers usually make money these days. They make money by generating tokens. Token is word, images, the video that AI produces. So the metric that matters going forward is going to be token per second, token per watt, and in the data center could be token per megawatts or even gigawatts in the future. So the facility power caps are fixed. So the more tokens per watt means more revenue, full stop. And that's the business model they have. And now the industry has been very clever at squeezing efficiency out of software, because that's one of the ways that you can create more tokens. So they went from FP16 all the way to FP4 in the past few years. They kept shrinking the numbers, using fewer bits to represent each calculation that they have. That helped them to save power. They consume less power. That was less work for them. And also, they got smarter in dynamic execution. So what it means is they use high precision whenever it's needed, and they start cutting corners whenever they don't need. That means less work, less power consumed. And also they minimize how much data movements that they're going around, right? By having faster on-chip memories. But here is the hard truth. You cannot go below FP4. Your model will lose its accuracy, its reasoning accuracy. The mathematics will break down. So the software is hitting the wall. So we have to see what's next. Everyone is talking about connectivity. That's one way. The memory wall that you heard about it, that's another thing. But the next gain to me has to come. I'm a power guy, so I say it has to come from hardware, especially from how we deliver power to the chip. So now let's look at the legacy power architecture. That's the way that today's almost majority of the hyperscalers, that's the way they are powering their systems. So the 40-volt comes in, it travels across the motherboard, gets a step down to a lower voltage to sub 1 volt, then travels through substrate, through package, to finally reach the ASIC. Every inch of that journey bleeds energy. Bleeds energy in board traces, in solder joints, the substrate. And by the time that it reaches to transistors, depends on the power level, you'll be losing anywhere from 15 to 30% of that power. That would be your PDN losses. It's RI square. The more powerful, if you go from 1 kilowatt type of XPUs to 3 kilowatts XPUs, that would be next generation. The current goes higher. You have resistance in the path. RI square losses, that means more losses that you have. So just imagine you have a 50 megawatt data center now. A 50 megawatt data center. That's the budget that you have. Just pick that number. After accounting for coolings, for facility overhead, let's say that the PUE is 1.4, what it gets to the server, to the compute portion, is close to 27 megawatts. And let's pick between 15%, 30% we are claiming here, 20% of it. That's almost 5.6, 5.7 megawatts of loss that you have. That's lost on the board as a board hit. Generating zero token will be zero revenue. This is not scalable, especially for next generation when we go about multi-kilowatts type of XPUs. So what's the solution? The solution is vertical power delivery and IVR. So here I'm showing only two stages of IVR adoption. And I want to be clear, I'm not comparing this with legacy. This is two different implementation for the IVR. It could be also on the LAN side and also could be embedded into the motherboard. I'm not showing those configurations here. So the one on the left is the near-term implementation, where we can put our IVR on the backside of the board, and we can achieve significant PDN losses. You saw all those resistance in the previous one. You have just a small resistor, the path to get to the ASIC. So you are gaining some of those losses that you had. On the right side is the ultimate goal. That's the industry ultimate goal, to go inside package. But there are some challenges. There has to be some sort of co-designs in order to, from the thermal challenges, all those has to be solved. And this architecture is the one that delivers almost 85% less PDN losses. And that's a huge number. And this is not the only benefit here. By bringing the power on the backside of the board under your XPUs, you are opening more space on your board. That would be for your bringing the high bandwidth memory closer to your compute. So every watt that we are recovering here is a watt that you can redeploy to generate more token. Again, we go back to the revenue. What's the business model of the data centers there? But IVR doesn't just fix the static power loss problem. It also solves the dynamic problem. If you look at the picture on the left side, this is a transient performance comparison between a legacy VRMs, the one in the red, and the blue one is the IVR. So if you look at the IVR, it responds really fast and recovers very quickly. Here we use 1,000 amps load step in 100 amp per nanosecond slew rate. Extremely fast. And if you look at the legacy VRM, it's slow because the switching frequency of these systems are really low. I mean, compared to this type of dynamic loads that next generation the market has to deal with. And it requires a big voltage guard band. So what does it mean in terms of the dynamic guard band? The equation that we have there is CV squared. So if we have 100 millivolt reduction in a 0.8 volt core voltage, that's roughly 20 to 24% additional loss that you have because of those guard banding. That's a dynamic power that you would have. Now look at the picture on the right side. The blue line is the IVR, is tracking the workload perfectly. It's full power when it's needed, it's near zero during the memory time. But legacy one, always lagging, is constantly burning power. So now, when we use IVR reclaims that guard banding, it minimizes the guard banding. If you can see it here too, it's like really a small voltage drop that you would have. And that wasted power, when we reclaim it, it becomes reclaimed compute. It becomes, again, revenue. Now, let's summarize what are the benefits really of IVR. Just like 3 layers that we go through. One of them, the first one would be definitely the PDN recovery. That's 15 to 30% of the server compute. That's what you are reclaiming. The second one was the guard band elimination that we discussed. Gives you additional 10, 25% token per watt if you can reclaim it. And the third one is the per core voltage granularity. That allows you to drop the idle core voltage to near zero instantly, which means further power saving. So now we talk about all these benefits. Let's put some dollar figures on it. We talk about the 50 megawatts, let's say 20% only PDN losses. Let's assume only PDN loss in these calculations here. I'm not talking about the benefit of guard bands and also per core regulation there. That was, the IVR could claim 5.4 megawatts, right? That was the number. Assume that you have a utilization of 50% and you are paying 50 cents per million tokens. That's roughly $2 billion. If you use H200, it could be 2.6 billion or more if you use B200. But here is the number I want you to remember, not the dollar figure, because that depends on utilization and also depends on the pricing, right? Because the whole like million token per watt could be anywhere from 50 cents to $2 per million token, or even higher, or even lower, right? That the price is changing. So that's not the number I want you to remember. IVR reclaims, in that scenario that we discussed, 20% of your compute power. That means 20% more token, 20% more revenue from the same facility, from that 50 megawatt facility that you had. It doesn't matter if that facility uses H100, H200, B200, you will have 20% gain in your revenue. So everything I said about IVR in the cloud applies also to edge. But the constraints are much harsher actually in edge or physical AI. You have a fixed battery. You have zero tolerance for latency. At edge, wasted power doesn't cost you revenue. It costs you the mission. Think about a drone that runs out of battery mid-flight, or a robot or an autonomous driving vehicle throttles mid-operation at the wrong time. It's survival, the latency in these systems. IVR eliminates both problems. Less wasted power means longer battery life, and nanosecond response means zero throttling. Two different markets, but still one solution can be applied to both. But the question comes in, okay, what do we need to change? For large-scale adoption of IVR, we need a new working model across the industry. So the existing model that we have, just to give you an example, power delivery is afterthought. So chip designers, they would finish their silicon, they hand it off, and then tell people, go figure out the power, how to power it. That model worked perfectly well so far. The power level were low. You could still do things on the motherboard side, and the power, as I said, were relatively small. But when you bring IVR inside the package, that model breaks down. You cannot design the chip first and then figure out the power later. Lots of decisions have to be made on day one in the same room by everyone at once. Chip architect, package designers, IVR team, even the EDA tool vendors, they all have to come together from the start. And the companies that they crack this collaboration model first will define the next decade of the AI hardware. There are some companies that they are already doing it. They are putting that ecosystem together because that's the only way you can benefit from IVR. So IVR, as we discussed today, is inevitable. The physics demand it, the economics of it, we discuss about it, it makes sense. The only question is who gets there first. So let me leave you with 4 things to remember here. First, power delivery is no longer downstream, it's day one. I told you guys, AI made power sexy again. So it was a day one that it has to be there. Second, the IVRs are evolving from a niche technology to a necessity. That's for next generation, you need it. This is not a future trend. It's happening now as we speak. Almost majority of the hyperscalers, they have their own IVR strategy now. The third one, the nanosecond scale power management will enable the next phase of AI scaling. No more software tricks, it's hardware. There are lots of opportunity that is there we can grasp here. And fourth one, which is the most important one, without IVR, future of compute growth is constrained by physics. My friends, the grid cannot keep up with the AI demand. We show you it in the first graph. The only path forward runs through smarter power delivery. And thank you.
感谢 Davud Yazdani 先生精彩的分享。